Cool. All right. So we've talked about, let's see, what are all we've talked about, let's see, what are all the things we've covered? We covered IP addresses. We covered how IP packets work. We've covered how your OS decides if your destination IP address is on your local network or not. And we also covered direct delivery. So if you are on the local network, how does a packet get delivered directly there through the link layer? We talked about ARP, the address resolution protocol, which maps IP addresses to physical MAC addresses. And then we talked about ARP poisoning or ARP spoofing. So we showed that like the fundamental basics of networking, ARP has no way of knowing, its really important job is to map an IP address to a physical MAC address, but it has no way of verifying that that's actually true and that actually happens. So this is something that we need to do that as an attacker, we can take advantage of in order to pretend to be other devices on the network. We can even, so we looked at ARP spoofing, we can even do similarly IP spoofing on a local network. So we can send a IP packet from one host to another, but impersonate the destination target host. Sorry, I'm a little bit hot. I need. Cool. Okay. So, so our goal here is we want to be able to send an IP datagram. And so I don't know, Christian, are you out there? Can we use you again? All right, cool. Thank you for being a good sport. Fun fact, there's a Christian in both sections. So on the rewatch on Tuesday, that Christian was quite surprised that they got, that they were getting chosen to represent a bad guy. Yeah, we'll have to have you all fight at the end so we can figure out which one is the real Christian. So cool. Okay, so and similarly, like what we did with ARP, so we looked at the network, and we go back to the network that we had. We talked about, we have my machine, which is 192.168.0.10, and the printer, which is 192.168.0.20. And when we get in, so we looked at direct delivery, how that works. When we send that, so let's say the printer gets an IP packet. And so now we're on back to IP. So let's say, there's M, there's P. We'll just keep this kind of simple right now. P gets a packet, and that packet will be composed of multiple layers because it's Ethernet. So the outermost layer, the source, let's say, has the MAC address of M. The destination has, so if it's going to P, what's the destination MAC address going to be? Yeah, MP. And this is so we've already established, so we can assume that M is already established ARP because this is now an IP packet that's getting sent there. So the outermost layer is Ethernet. The innermost layer is also going to have a source and a dest. So the source here is going to be M192.168.0.10 in our example. The destination, what's the destination going to be? You don't have to give me the exact IP address, but is it going to be MP? Yeah, it'll be the IP of P. Great. It's not MP, right? Because MP is actually 48 bits. That doesn't even fit in the IP. So it is, and this is a big callback to when we originally designed this crazy network. The destination is 192.168.0.20. Okay. Here's what we can do. This will actually bring us back. I think both classes enjoyed the concept of printing currency. And the message is print money. Only 3. We don't want to be too greedy. So that's the body of the message. So the printer gets this. So, and just to be clear, this is the Ethernet headers. This is the IP headers. And for right now, we can just call this will be IP data. Questions on this packet? Cool. Okay. So I've set up my printer. I've set up my printer very secure. I have a policy that says only print from 192.168.0.10. Right? Sounds good. Printer gets this print message. Should the printer start printing? Yeah. So it passes the policy. It says only 192.168.0.10. Great. Prints. The printer starts printing out money. The printer itself detects that. It calls the FBI. The FBI busts into my house and arrests me for being a currency forger. And I go, hey, I never printed currency. What the heck's going on? And they say, hey, but you have a policy here that only 192.168.0.10 can print. And your machine has that IP address. And therefore, it must have been you that sent this, right? Now, is that true? Am I the only person who can send that packet out? Yeah, why not? So imagine, Christian, I'm going to use you again. How do we know that Christian's not on my network? Think about it like this. What's stopping Christian from sending out a packet that looks exactly like this? Yeah, absolutely nothing. Christian, don't talk about ethics. You don't have ethics in this example, in the notability world. I don't want to hear about your real life. This is getting too weird. Okay, so yeah, so fundamentally, there's nothing at anything we've talked about, and there is nothing secret that I've been holding back. The switch can't tell that this is that Christian is forging this packet, because for all the switch knows, maybe M did switch to whatever port C Christian is now using. So that doesn't even really matter. And so fundamentally, and this is the fundamental problem. So let's look at this packet. So you're P, you're a printer. What of this packet can you trust? Let's look at the Ethernet headers. Can you trust that this was sent actually from a source address of M lowercase m? Nope, because nobody validates that on the way. You can't trust that. Can you trust that the destination is the MAC address of P? Yep, that's good, right? Why do we know that this is good? Why can we trust this? Well, that's a real terrible color. Yeah, because it's for us, right? Otherwise, we wouldn't get it. Exactly. Okay, then we think about the IP packet. Can we trust the source of this IP packet? No, we can't, because fundamentally, anybody could put any value in there, and we wouldn't know what their actual quote, their assigned IP address is in the network, because nothing's stopping them from doing that. What about the destination? Can we trust the destination IP address? In some sense, yes. Similar logic, because it's meant somebody is trying to send this to us. We don't know where it came from, but we know it's actually coming to us. There's actually a fun analogy with, surprisingly enough, phone calls in the telephone network. So what are you supposed to do if you get a phone call that's allegedly from your bank saying that there's been a problem with your bank account? They're going to have to lock it down unless you can verify that you still have possession of your card. Yeah, can you trust the caller ID that shows up on your phone that says this is 1-800 Chase? Yeah, so fundamentally, the telephone network works actually in the technical reasons are super interesting. We've studied this in some of our research, where the reason is that actually having caller ID was optional for a long time in the telephone network. So it got added as an optional header, and nobody along the call path actually verifies that and authenticates that that caller ID actually belongs to the person calling you. And so, yeah, somebody's mentioning in the chat that they downloaded an app that allowed them to spoof their caller ID so they could call somebody from their own telephone number. It's the exact same way on IP. You can technically, I guess, send an IP packet to somebody from themselves. And so, yeah, the other thing that you'll see is, I'm sure you've all gotten what they call neighbor spoofing telephone attacks, where they will call your phone number with a phone number that has the area code and at least 4 or 5 of the first digits the same, and of your own phone number. And I think that's preying on people thinking that it looks like their own number, so they answer it. And they can randomize that every time and change it for every call, so it makes caller ID based blocking basically useless. So anyways, there's actually a lot of interesting parallels between network security here and how networks work and how the telephone network works. Cool. Yeah, they are super annoying. We're trying to, we do some research into stopping that, so that's cool. Anyways, so fundamentally, the only things that at the Ethernet and the IP level that we can trust are the destination. Did the destination get there for the IP? And this is similarly with a call. You can't trust the number that you're calling from, but you can trust that the telephone network, when you try to call Chase or whoever your bank is back, that it will actually go to Chase. If they could hijack those calls, they would be raking in the dough. So. Okay, cool. So this is how we can perform an IP spoofing attack, and it works. It's literally trivial. So we can pretend to be another host on the network. So in this example, Christian has the IP address 111.10.20.121, and they want to send a packet to .14 in this network, pretending to be from this phone .16. So there's some trust relationship here. And so then Christian just creates this packet and can even, this is kind of the crazy thing, they can even lie at the Ethernet level. So they can set the MAC address to be their MAC address and send it to the target MAC address. Because again, nobody's checking that, so it really doesn't matter. So this is how you can do IP spoofing at the local level, and we'll see how this can be extended further on. Any questions about this? Cool. Okay. Now we got to go beyond into the wide, wide world of the web. Do we have a diagram for this? Kind of. Is it super annoying when I scroll up and down between these things? Okay, thanks. It's like refreshing the material in your head. Sorry, Colin, you got outvoted, so be quicker next time. Okay, cool. So we've seen, and actually what we've seen is my machine here talking to either an Xbox or printer or anything on the local network. So everyone agree that we all understand how a packet gets from one machine to another machine on the local network? Yep, cool. Now we just have to figure out how a packet gets outside of our network, and that same process happens at every single hop along the way. And that's exactly how the internet works. So the packets that are getting sent right now from my machine to Zoom are making all of these local hops. And so we have to change this diagram slightly. Basically, so what's missing in our current network diagram? This one. Right? We have our machine, we have a printer, all these other devices connected to the network. But how do I actually get to the internet here? Yeah, I need some way to get out of this network, right? So remember we had that decision tree here. I want to send some data to an IP address. We say, is this IP address local? Then yes, I know exactly the procedure to follow. I make this ARP request, I do all of this. So But we haven't studied the what if it's not local. And actually in this network, so to get some things to work, like let's say your printer, technically your printer doesn't need access to the internet. So you could be printing, you could be printing documents and not currency because you're not a criminal. You could be printing documents, let's say Amazon return, whatever, barcodes or whatever the thing I'm thinking of, return forms or whatever. You could do that without the internet at all. Labels, thank you. How did I not remember that? Yeah, so you don't even need access to the internet at all to do this, right? And this would all happen locally. But of course, we do want access to the internet. So the way this works is we're going to take our diagram and we're going to change it ever so slightly. So we're going to have our machine. And now I'm going to deliberately keep this as a switch. Oops, hello. Hello again. Okay. Oh, man. There we go. Okay, we'll add in the watch for now and the printer, but I don't want this to get too complicated. And we're going to add in another special device we'll call R for router right now. And there's really nothing special about R. And this is why I want you to kind of start deconstructing in your mind the notion of a router being this, this Wi-Fi box or this box that also does switching. Because it can do different kinds of things. Because a router can literally just be a machine, as we'll see, with two network interface cards. And that's all that's basically required at a basic level. And when you realize that, then it allows you to set up your own machine to act as a router so that you can give access to, let's say, a local network that is not accessible through Wi-Fi on your own machine and all this kind of stuff. Yeah, so we can go with our network. So the router is probably connected to, we'll call it our modem, which is then connected to, and now I'm going to draw it as a squiggly thing because I have no idea what goes on in there. And we'll call this the ISP. At some point, it'll come to another ISP. And then it'll come to a router, which is connected to some kind of switch, which is connected to Zoom. Cool. So we'll still have our same network. So I'll be 192.168.0.10, and it was a /24 if I remember correctly. Is that right? So let's say Zoom, because the problem is, I guess, all of the nice IP addresses are taken. We'll do all twos. How does that sound? Oh, twos are like Z's. That actually makes sense, maybe 2.2.2.2. So that's not actually Zoom's IP address, but let's say that's the IP address I want to send an IP packet or IP datagram to, right? Or IP packet to. So we'll just walk through this exactly like before. Right. So what I know about the local network is my IP address 192.168.0.10. I know the net mask is /24. And so just like before, we'll say I want to send data to 2.2.2.2. Okay. So now it'll ask, is 2.2.2.2 local? So what do you think? No, it's not local. Otherwise, why the heck would I do this insane example? Okay, but now we don't know where to go. So why in this diagram is the router special? Like we can already kind of see it in this diagram. What makes the router different than the watch or the printer, or even my machine? Yeah. So thank you. I think Amadeus and Eric in chat just mentioned that it's our way to get from local to the internet, right? Or it's the only way. If you think of this as you all have studied like graphs and trees, right? Yeah, so it's the only way. So we're a little connected network in there, right? With our switch. There's only one possible way we could get out of this local network, and that's through the router, right? That's our only connection to the internet. So it must somehow be important. But so we need to know that. So we actually have upped the information that we need to know. We need to know our IP address, our net mask, and so we need, now we need IP, net mask, and we'll call it right now a gateway. But this is actually a very general approach that we'll kind of come back to in a second. So we say is 2222 local, and basically say, okay, where to send 2.2.2.2, because we could think, hello. We could think that in this case, this makes sense, right? We have a router with one modem to one ISP, but if we're running a business, right, our router actually may have a second modem attached with a different redundant ISP, which has its own connection there. So I may have different rules about which IP address I want to use through which modem and which ISP. Maybe it's actually cheaper for me to send certain traffic through certain ISPs. And that's why routing itself, the idea of, and routing is basically the notion of, okay, I have this packet, it's destined for 2.2.2.2. Where's the next hop? In a local home network, it's simplified basically by the gateway. So your gateway is the next hop. So here I know my IP 192.168.0.10/24 is my net mask, and my gateway I'll call 192.168.0.1. So this means that, and by default, the gateway says, okay, if you don't know where to send this packet, AKA it's not on the local network, then send it to the gateway, and the gateway knows how to route that packet. Yeah, and then it's their job. So what's a requirement? Can I have a gateway of 192.168.10.1? Why does it have to be on the local network? Yeah, so I can send the packet to it, right? Basically, what I'm gonna do is leave the IP packet the same, but send the packet to the router. Yeah, otherwise there's literally no way for me to get there. So it has to be something on my local network. Yeah, that's an important point. And this will help you out if you're ever setting up a machine and it's giving you like an invalid gateway error and you're like, what is going on? I don't really understand. It's because you've messed up the net mask. So the net mask doesn't actually match the network and your gateway is not in there and things are failing very poorly. Okay. So we say, okay, where do I send it to 2.2.2? This is basically the routing question. And so what's the answer in this network? Where do I want to send it to? I want to send it to 2.2.2, but where do I? Yeah, I need to first send it to R. I need to first send it to the gateway. So this is 192.168.0.1. Okay. So where to send? So the answer is 192.168.0.1. Okay. So I need to think about what we actually want to send. So ultimately, what's the IP packet I want to send? So what's the source? RIP? Yeah. So this will be, and I've messed up because I've used internal IP addresses here. I'm trying to decide if I want to cover NAT a little bit. Okay. Let's do it very briefly. Okay, source 192.168.0.1. And the destination is so would the destination be 192.168.0.1? Yeah, no, because I want my ultimate destination is 2.2.2.2, right? That's where I want the packet to go. And then I have some data in there. This is my video frame. But the next hop needs to be 192.168.0.1. And for the next hop, so I know that 192.168.0.1 is on my local network. So I'm going to need to wrap this IP packet in a direct delivery of this IP packet. I need to add an Ethernet header. So what's my source Ethernet header? Yeah, MAC address of M, perfect. And the destination? How do we get the MAC address of R? Yeah, I need to ask with ARP. So I need to say ARP, what is 192.168.0.1? That's supposed to be a question mark, sorry. There you go. Right, what is ARP? ARP, it's not a pirate protocol, ARP, okay. And it will say, it will return us the MAC address of Z. And so then I put here in the destination, MAC address of Z. And so I go back up, I'm M, I send this out to the switch. The switch says, and we actually know, so the switch is keeping track, and because these machines just communicated using ARP, there'll be entries in our switch port. So will the switch send this packet out to every device on the net on the switch? Nope, it'll send it out only on the port that has the router. So the packet goes from here to here. The router gets it. It says, is this, so the router gets this whole packet. It says, is this destined, is this, at the Ethernet level, it says, is this destination for me? Yes, MAC address of Z, great. So it will then take off that whole layer. It says, awesome. And then it says, is this IP address for me? Is this packet meant for me? Nope, it's not. And so it needs to know its routing table that says, okay, if you have a packet, so the router needs to know, let's call, oops, low. What's supposed to be MR, sorry. Ah, wait, yep, good call. Thank you, somebody messed me up. MER. Yeah, so this should not be the MAC address of Z, otherwise it get dropped. It is the MAC address of R, right? The router. So we fundamentally, so if you think about it, ARP only happens on a local network. Do we have any way to ask about the MAC address of Z? No, no possible way. The only device in this entire diagram that can ask for the MAC address of Z is Zoom's router, which is way the heck over there. I have actually no way to even talk to that router itself. Cool, okay, great catch. So our packet travels to the switch. The switch then travels to the router. The router looks at that packet. It looks at the IP address. So it takes off this outer Ethernet layer. And it says, okay, is this IP address destined for me? Why does the router care if the packet is destined for it or not? Yeah, to know where to drop it or to know to reply to it, right? So this is why when you access your router's IP address directly, often it shows you a web interface where you can configure things. And that's how it knows, because your destination IP address is that router, whereas the whole other time you're trying to use the internet, your destination IP address is not that. So it looks at that and it just routes it along its way. So your router actually, so the very cool thing is this behavior that happens on your machine that decides where does a packet go when it's not local is something that happens exactly on the router, and it's the same process. This is definitely not something we're going to get into the weeds with. That's something that you can study in your networking classes. But essentially, this router will have something that says, if, so we'll call this interface 1, and this one interface 2, because I don't want to use 0 and 1. Basically, it'll have something that says if 192.1, and it's the important thing is if dest is 192. Actually, it'll be a starts with, but whatever. .192.168.0, then send on interface 1, else, well, it'll be like an else if dest. Actually, in this case, it's just an else. This is why I see we're not going to get into this. Send it out to interface 2. Send it out to interface 2 to whatever the IP of modem 0 is. So this is, we talked about it very briefly, like DHCP. So this is actually why your router, if you go in and check the settings, your router depends on the specific ISP. Sometimes you have a fixed IP address, sometimes not, but oftentimes it uses DHCP itself to get its external. So this is usually called on a router, the WAN side, so the wide area network side, and this is the LAN side. So then your router says, okay, I need to send this to IP of the modem, which it now knows because it knows its gateway and where it should send packets. So it does exactly the same thing. So at this point, our frame of reference has just shifted. And now we're focusing here and considering these two devices as a local network, but direct delivery happens exactly the same way. So your router needs to figure out the MAC address of the IP of the modem. It figures that out through ARP. It then will take this packet, add a new Ethernet frame to it. The source will be the MAC address of the router, and the destination will be the MAC address of the modem. And then that's how that packet goes from the router to the modem. So it goes here. And then the modem sends it to the ISP and does all kinds of stuff. And now, do we care or actually know anything about what they're using in here? Are they using Ethernet or IP addresses or anything? Do we even really care? No, we don't care. They could be, it could be carrier pigeons. I don't care as long as they get my packet there, right? And even then, I don't have a guarantee that they will. But and then at some point, it will cross ISPs. So it'll cross from our ISP maybe to somebody else, to some other internet service provider. It'll finally come to the router at Zoom, where the router at Zoom will say, okay, is this for one of my packets? Do I know how to get there? 22222, yes. For me is, and let's say this is a 2.2.2.1/24 is that IP address of the router. So the router says, okay, yes, this is for my network and it's on my local network because it's 22222. It starts with 3 2s. And so I can do direct delivery here. The router uses ARP to say, finally, so it gets this packet. It uses ARP to say who has IP address 22222. What's your MAC address? And that Zoom machine will respond. So finally, the packet will arrive. The MAC address of a ZR for Zoom router, and the dest will be the MAC address of Zoom. Finally, that packet gets to Zoom. Zoom gets it. Now, does Zoom, again, similarly, does Zoom know about my MAC address? Yeah, no, because that information gets stripped off at every single step, right? That doesn't make it out of my local network because it doesn't need to. That MAC address information is only used inside my local network. Cool. It gets it. It looks at it. And that whole process was just to do one frame of video. And then that keeps happening with all of this. This is how the internet works. I mean, this is how literally how your packets are getting from me to Zoom and then from Zoom to you. It's crazy. Yeah, I can't believe how fast this happens and how actually reliable this is in practice. So, think about this a little bit when you happen to get some instability in your network. You can say how much it sucks, but yeah, it's still super crazy that this happens and that everything actually still kind of works. Cool. So yeah, this is why indirect delivery is actually nothing fancy. The only fancy thing is this routing part. And the other fancy thing that has to happen, which we'll get into really quick. Normally, I don't cover this in too much in depth, but since it's such an important part. So why was the 192.168.0 network important? Why did I say that that's why I chose that? What's special about 192.168? Yeah, it's a private IP address range, which means when Zoom gets this packet, they'll say, I don't know how to reply to this packet because I can't talk to that IP address. It's a private and it's a local IP address only. So there are literally probably, if not thousands, probably millions of machines out there who think their IP address are 192.168.0.1. So NAT is a fancy thing. That does network address translation, which essentially sits, your router is smart enough to know that, hey, I know the local network and I know my public IP address. So you'll have a, so some public IP address. And so essentially when the packet crosses from your local network and your router out, it will replace your private IP address with your IP public address, and the packet just goes out. And it does it in a very clever way using some extra information that we haven't talked about, but essentially it encodes information in there so it can do the reverse when it comes back. So when your reply comes back from Zoom, it looks like Zoom's replying to 192.168.0.10, and it keeps track of all of that. So anyways, that's how network address translation works. And this is actually why we kind of haven't run out of IPv4 devices, because your house really only needs, if you're not running a service, so as we'll see on the network, to run a service, you need to be connected. So people need to be able to connect to you like Zoom, right? People in this case need to be able to talk to 2.2.2.2. They need somewhere to send their data. Due to the magic of NAT, you don't need a public device for every single device inside your network as long as you're not accepting connections. Now, where that maybe ties into another thing is, and we haven't even talked about ports, but you can think of port forwarding as a way to accept connections. Now, the problem is if you have like Xbox here, and you want people to be able to connect into your machine, so you're trying to run a server, you need a way to tell the router, hey, when you see packets like this, send them to the Xbox because somebody is trying to connect to me and I want that to happen. And that's basically to get around NAT. So all of these, so it's super funny. We like developed network address translation so that we could deal with having many devices on our local network without having to worry about having public IPs for them. But it's like we want sometimes somebody to contact us, so we have port forwarding. But port forwarding is actually a super pain to set up. So there's stun and turn are all ways that you can try to basically automatically set up port forwarding. There's also other things. Anyways, all kinds of crazy stuff. So yeah, that are real world things that actually do this. So let's look at this indirect delivery example. So the gateway is, and the other thing I didn't mention in this diagram is that I said that the IP level of the packet doesn't change. That's kind of true, right? There is actually one field that has to change, and that is what we talked about, the time to live. So every single hop, that value gets decremented, and when it reaches 0, the packet is dropped. And so that's so that the packets don't live forever in the network if something fails. Cool. All right, so let's look at this example. So again, indirect delivery, we're on 2 different non-local networks, right? And we know that, and we're able to tell that. So we need to send our packet to our gateway. And the gateway is just a machine that is connected to at least 2 or maybe more networks. And so it has to figure out which way the packet goes from there. And this process just continues network to network until somebody finally gets us to a subnetwork that has the same destination as the host. Cool. All right, so here we have another example. We'll briefly walk through it where we're trying to send this packet from 111.10.20.121 to 128.111.41.10. And we'll see that that packet gets sent from switch to switch, or essentially here we're using it as routers. So from router to router to router to router, all the way there until it gets there. And the important thing is the TTL field is decremented at every step. The link level addresses and headers change on every step. And the interesting thing here, this is where networking gets super complicated of how do you decide to get a packet to the closest destination and continue it going here. It may surprise you, and this is one of the fun facts I love about networks, that so if you were to just think about number of hops, did this packet take the least number of hops? No, is there a shorter path? 1, 2, 3, 4, 5. 1, 2, 3, 4. What's the shorter path? Yeah, the shorter path is up here. Right there. 1, 2, 3, 4, 5. So 5 hops. So does this ever happen that a packet can take a longer route there? And again, remember, things are fast, right? But they still, every hop has to do some computation and some work. It's not free. And these routers may be in completely different physical locations. So so if you're choosing optimally, right, you actually maybe never want this to happen, but why might it happen in practice? Yeah, maybe traffic. So good ones are maybe the network knows that this link is saturated and it can't handle any more traffic. So the shorter path, there's something wrong with it. Yeah, one of the most fascinating ones is, let's say this router represents an ISP and it's trying to decide where to send traffic, and it's cheaper. It's all about those dollar bills, right? You should think about that. These are companies, right? So it's actually cheaper for it to send it out on one path than the other path, because ISPs have agreements with each other, and it's actually gets very complicated of how this all works. And it's partly complicated because of the fact that it's a business relationship between them. So that actually literally factors into these routers' decisions of where to send packets. So that's sometimes why a packet can take longer to get there, and the other crazy thing is these monetary relationships aren't always symmetric. So that means that when the packet goes from 121 over here, it can go this way, but there's absolutely no guarantee that the return packet travels that same way. For this person, it may be cheaper to send the traffic this way. And so when the reply happens, it goes back this way. Absolutely crazy. And so add those things to the reason of why it's magic that things kind of work. Cool. Okay. Okay, so some fun historical facts. Obviously, so right now, like I mentioned, we do hop by hop routing. When the internet was smaller, they actually envisioned a reason why when you're sending a packet, you may want to choose your route through the network. So why would you want to choose your route through the network? What would be an example? Yeah, so security or privacy. So you look at it in multiple ways. There used to be stories of, I don't know if it's true anymore, but people, you can trace and time, actually, there's a whole area of networking research is understanding what's actually going on in the internet. And people are able to determine that packets sent, let's say from like Germany to, or Russia or whatever, to other countries, for some reason made a stop in the US before going back out. So the theory that the NSA was listening to that traffic is, who knows, draw your own conclusions. But anyways, if you had source routing, you could choose to avoid that, right? You could think about countries that do censorship, these kinds of things, right? Is you can think about that. So yeah, it's super interesting. So, okay, I'm not gonna go in depth in here, but if you want more information about routing, this is what I mentioned. You can actually look in your, you can use this command route-n. This does not work on Mac. It, for some reason, it uses the netstat tool. And I even think route is deprecated. I think it got moved into the IP command on Linux. So this is slightly out of date, but basically the way to read this is it says, hey, if you don't know where the packet goes, so the destination is anything, and this is kind of a top-down approach, send it to 192.168.1.1. But I'm going to skip these. Cool. All right, questions on indirect delivery. You now understand how packets move through the internet. Isn't that crazy? It's like, what is it taking us, 3 courses? Cool. All right. So now we're going to talk about TCP, and we're going to add that layer to the top so that we're going to actually start getting closer and closer there. So going back to the layers, we've looked at the physical layer, we looked at the link layer, we looked at ARP. The one thing I didn't mention was RARP, I guess, reverse ARP. So reverse ARP is basically goes, so what's the input for ARP and the output of ARP? The input is what? What's the input of ARP? Let's think of it like a function. What do you give? No, like conceptually, not the IP. Yes, you give it an IP address, and what does it return for you? A MAC address. Awesome. So reverse ARP is the opposite. So you give it a MAC address, it returns you an IP address. It's a way to ask a machine on your network, say, hey, what's your IP address? I see your MAC address. So anyways, it's kind of a nice thing. At the IP level, so at the IP level, we didn't go into it in depth, but there's various protocols here at the IP level. One of those is ICMP, which is a ping packet. So when you send ping, it's sending it at the IP level. And now we got to build up. So think about this. We built up all of that knowledge and machinery and understanding just to get a packet from one IP address to another. right? We had to build all of that local stuff. We had to build all the physical stuff. We didn't build the physical stuff. We used it, whatever. We had to understand how packets moved locally and then moved from hop to hop. Now we want to do stuff with it. So we want to actually send data. So this happens at the transport level with TCP and UDP. And we build applications on there. We're going to start with UDP because it's the simplest. So UDP builds on IP, right? So just like that stack that we looked at, it uses IP to provide a connectionless. So again, no concept of a connection. You're just sending packets. Unreliable, best effort datagram delivery service. So again, we have delivery, integrity, non-duplication, ordering, and bandwidth is not guaranteed. None of that stuff is actually guaranteed. But what it adds is something super important. So we've been thinking of IP addresses like physical mail addresses, right? So you can think of that like the street number when trying to mail a letter. But how do I mail a letter to an apartment building? I think some of you are maybe in apartments. I think that's probably a fair guess. Yeah, I need some other bit of information, right? I can't just send a letter to an entire building. I need to send it to a particular place inside that building. And this is what TCP and UDP provide, which is this notion of a port abstraction. And why this is incredibly important, let's say your IP address is Zoom. Oops, hello. So you are Zoom 2.2.2.2. Too many twos. 2.2.2.2. Zoom. What kind of services does Zoom have? So we saw that there's like a meeting service, right? Video, let's call it video chat. Text chat. What else does it have? Audio. Maybe the website, right? So again, we saw that packet, right? That so I sent an IP packet from my IP. The destination is to 2.2.2.2. Now the question is, how the heck do I specify which of these services should get it? Because if my video frames are going to the text chat, that would be very, very bad. So that's why we need this concept of a port number. So you can think of an IP address specifies the street address, and the port number specifies the apartment number. And so that's why, so you can think of having different services in here, and that's how the operating system is able to know which packets are meant for which service. Cool. So UDP is still used a ton. This is what we talked about. So we'll compare and contrast it to TCP a bit later. But a lot of things, actually, so incredibly important things. So DNS is the thing that maps Google. So just like, remember, ARP was a function that took in IP addresses and gave you MAC addresses. DNS is a function that gives you a domain name and returns whatever the IP address of Google is. Yeah, that's one of their IP addresses, but tons of stuff. But so yeah, so services like DNS, which also underpin the entire internet, if they fail, that's a massive problem. Use UDP. Other things like this video call that we talked about, because it can handle dropped packets, and you actually don't want that for real-time things. Games also use DNS, all kinds of cool stuff. So just like everything else, this shouldn't surprise you. There's a header for UDP, and there's a specific format for a UDP message. So it leads with the most important addition here, the source port. So there's 16 bits. How many different source ports are there? 2 to the 16th, what is that? Somebody type it out, please. Yeah, 65,536. So it can, so this number can be 0 all the way up to 65535, right? Because it's one less. So it's 2 to the 16th minus 1 is the highest value because you have to include 0. And the other 16 bits are the destination port, the message length, a checksum, and then the data. So this is why UDP literally adds nothing on top of IP. The only thing it adds is the port abstraction. And so this is nice because it's not adding a ton of overhead, and it's not giving us additional features that we may not need. Cool on this? So the question is about ports. It's very different. I don't know how Zoom actually makes their thing work, so it's super difficult for me to say. Yeah, UDP. So for something like, let's say DNS, it needs to be on a port where everyone knows it, and so they can ask for DNS packets. Usually, yeah. So I'm not really sure. That's a good question. Cool. Okay. And so just like we saw with IP headers and the IP data being encapsulated inside of a Ethernet header, and that packet being the Ethernet data, the exact same thing happens here. So we have the UDP data, which is the actual data we want to send, like look up this request. What is this packet? We have that UDP data, and then we have those UDP header, which we just saw, which is very, very small. Then that is inside the IP data, and we have an IP header, and then that is then fit into the frame of the Ethernet packet, which is then has its own frame header. So it's like headers all the way down until you finally get to the data. It's actually pretty cool. I kind of like this. It's like a nice, the layers analogy makes a lot of sense here. And that's it. So there's nothing fancy to UDP. There's literally nothing. All that it adds is this port abstraction. And so for our purposes, what we want to think about here is how can we spoof an IP address? How can we spoof UDP packets? Well, does anything in here add anything to what we've talked about with IP spoofing? Yeah, fundamentally no. So the only new things are these ports, right? So let's say I wanted to spoof a UDP packet, and I wanted to pretend, in this case, I'm getting revenge on Christian. So I want to make a DNS request on behalf of Christian. So what do I need to control here? Or what does the DNS server need? Yeah, it needs the port. So I need the DNS port. Can somebody look that up? Is it 53? If you're on Linux, you can do, oh, that's too many L's. I think ADC ports is in there. Yeah, so port 53. So all I need to do, I can just do IP spoofing. I can set, but now this time my data is not a printer command. It's a UDP message. My source port is 53. My destination port is whatever. my source port is random. It's for me. So I should get rid of that. And this is where this lack of erasure is annoying. And so I set the destination port to be 53. I set in that packet, I set the IP source to Christian's IP address. And then I'm going to make a DNS query for, I'm going to get him back for the printer thing. So I'm going to make a DNS query for I am a currency. What's the word? Currency fraud. Why am I blanking on that word? Forger. There we go. I am a currencyforger.com. What's that IP address? And so I'm going to do that a bunch and fake a bunch of those DNS messages. So it looks to his ISP like he's a currency forger. His ISP is going to turn him in and bad things are going to happen to him. But I wouldn't really do that, of course, Christian. No, not you, the other Christian from the other class. And so this is how we can do that. So we can also leverage trust relationships. So I mentioned another protocol here. Oh, yes. Oh, no, not yes. I want to do that better. I mentioned another protocol here. What's NFS? Does anybody use that? Or have heard of it? Yeah, it's the network file system. If you've set up on the implementation that's usually used on, is SMB the same? No, I think it's actually different. So we'll stick with the NFS for now, but I think SMB Samba is very similar to NFS. It's basically a way like Samba or file sharing to say, hey, share this drive on the network. And of course, you may want to limit who can access that drive. You may want to say, only my machine can access, or my machine can delete files, but other machines can add files, for instance. And so that's why we may find ourselves in a situation where now we'll give Christian his due back. So now the server is here. There's a network file share server. There's a trusted client. And the attacker now wants to pretend to be the trusted client and spoof a UDP packet to the server. And let's say that message is delete all files. So the attacker can do this. What does the spoofed UDP request look like? So if we zoom in on that. So can we safely ignore the Ethernet header for right now? Yeah, let's ignore it for now. So we'll start at the IP level. So what's the source IP that Christian's going to put here? Yeah, client. And the destination? Server. And then so this is IP. And then at the UDP, so S port. So the source port, I can put whatever I want, ABC, and destination port. I'm going to write NFS for here because I don't know what that port is. If somebody can look that up, I will rewrite that. $20.49, thank you. Cool. So with this packet gets sent, and does it matter to the server whether I'm in the local network or not? Yeah, no, because it depends on this server and this client, right? If they have private IP addresses and I'm outside, there's no way I could get a packet in that would actually do that, right? Because the router would never accept a packet for an internal network. So it all depends on the specifics of the circumstances. But fundamentally, if I don't even need to be on their local network Christian can just send, an attacker can just, send this packet out and spoof, pretending to be the source IP of the client, the destination IP of the server. The server gets it and it checks it, right? It says, okay, where's this packet coming from? It's coming from client. Is the client allowed? Yes, the client is trusted. I trust that client. The packet's for me, great. I take off this IP layer. Next layer, the source port. Okay, it's for source port ABC. Great, don't care about that. Destination port 2049. Hey, that's my NFS service. Great. And so the operating system sends this data to the NFS server and deletes all the files. Now the server is going to reply. It's going to reply back and it's going to say, at this level, so at the IP level, what's the source of this packet? Server? Destination? How come the destination is not Christian? Yeah, because spoof. Thank you. Because the server has literally no way of knowing that this packet came from Christian and not the client. So all that it knows is that it went from client. So great. Now, a little bit more about UDP. So it's going to flip the source and destination ports just like it did the source and destination IP. So the source port now will be 2049 and the destination port will be ABC. Cool. So what happens when the client gets this? Oh, they only freak out if they're really careful. Yeah, so fundamentally, right? So a question to think about is how does this normally work, right? So normally we send a UDP request and the way that we know we're getting a response back is we look for a packet that has that is to that destination port. So you remember how we talked about with ARP, there's no way to link those two packets, but here we do know a way to link these packets because we chose that source port. So we choose it randomly and we expect that that same thing is sent back. And so we know this message is a reply to the request that we sent. And in this case, if we get a packet for something we're not expecting, we just drop it. We just say, great, okay, this is weird. Who would send me this? And like nothing, literally nothing happens with that packet. Does that make sense? Yeah, the next morning when the client checks the server, or when the client actually accesses it, they'll be like, what happened? And the server will gladly show them the logs. They're like, hey, trusted client, I deleted all those files like you asked. And the client will be like, no, I didn't. And then they'll have to figure out what happened. Cool. So this is spoofing, right? So the notion here is we're spoofing a trusted client to a server. Now let's look at the situation of we want to do hijacking. So this is the case where the client has made a request to the server. In this case, think DNS. So in this case, the client is asking, hey, what's the IP address of google.com? So why might Christian want to change the results of a query? So why might Christian want to change that response? Yeah, so Christian may want to change it from all eights to, I don't know. I don't know what a bad looking app is like. 1. There we go, leet. So 1337 or something, a IP address that Christian controls. That way the client thinks they're going to google.com, but they're actually going to Christian. So now in this case, the client sent a UDP request. So let's go through what that looks like, that UDP request. So at the IP level, the source is going to be what? Client. Destination will be the server. The source port, let's use something different, BCD. So it'll be a random thing that we choose. The destination port, what port did I say DNS was? Oh, 2049 was NFS. 53, thank you. So now for Christian to reply, what is the packet that Christian must reply with? Or let's think about like this. What's the server going to reply with? Right? The good packet. What's the good packet going to be? So what's the source there? Server, thank you. Nope. Destination will be the client. The source port will be 53. And the destination port will be what? BCD, thank you. 8.8.8.8, right? So that's the request that the server is going to send. So if Christian wants to forge his own request, what does that packet look like? So the source is going to be the server. Destination will have to be the client. The source port has to be 53. The D port, yeah, so thank you, you're getting there. BCD. And now 1.3.3.7. So everything needs to be exactly the same except for the payload, right? All the headers need to be exactly the same. What's the problem there? What problem does Christian have? So look at that packet that Christian wants to send. Yeah, what information does Christian not know to even construct that packet? So can Christian know the server's IP address? Yeah, of course they know the server's IP address. I know Christian uses this DNS server. Let's say yes. Right, I know this. I know the client's IP because I'm deliberately trying to target this client. I know the source port here, 53, because this is the server's source. So I know DNS is on 53. I know it's going to be there. What about this destination port? Where did that destination port come from? The client, exactly. And it should be randomly generated each time because that's what links the response. So what can I do? Well, what if I change the situation? What if I say I'm on the same local network as the client and the server? Yeah, so I can do ARP. I can ARP poison so that the client actually sends that packet to me first instead of the server, and I can just reply. Or I can do what we talk about. I can turn that switch into a hub and get that packet, right? Or maybe another thing I can try. How many source ports did we say? 65, 535. Yeah, why don't I just, what if I tried, what if I sent out 65,536 packets, each with a different destination port? Yeah, the client will just ignore all of them except for the one that we want. And I do, though, have to race this one because this one is also coming back, right? Excellent. Okay, this is great. Yeah, that took a little bit longer, but this is what I want to harp on. So, so you can see how these attacks build on each other, right? So we can think about the capabilities that we have. As an attacker, if we're on the local network, we can use ARP poisoning to steal that UDP request because fundamentally I need that port to be the same. And so I need a copy of that packet. Maybe I can try to guess it. Maybe it's not as random as I think it is, and I can break it that way. There's other ways to think about approaching this. But this is, and you can see this is a fundamental difference from UDP spoofing, where I'm pretending to be somebody else when making a UDP request. But to actually spoof the reply requires more work and requires me. I also don't necessarily have to be on the local network and use ARP poisoning. If I'm on the path, right? If I own any of those routers on the path that packet takes from the client to the server, then I can send that back. What's a case where you may be on a local network with somebody who's making DNS requests? Yeah, coffee shops, Wi-Fi, public unencrypted Wi-Fi is one of the things you should be scared of when using unencrypted communications because of what we talked about, ARP poisoning plus DNS hijacking. All this stuff is because these protocols don't have any sort of authentication or integrity here. So we'll stop here. We'll look at one more aspect of UDP, then we'll move into TCP. Now, of course, don't go away from this so terrified, right? There actually are mechanisms we've put in the web in the higher level protocols to try to mitigate this. But fundamentally at the core, this is what's happening. So thanks everyone. And that was fun.